Hello everyone, this is Priyanka Gharat from Silicon Interface. So today I am here to present a poster that is Diagnosis of Fault using Fault Simulation on PCI. These are the authors who has done a significant contribution in proposing this thought on diagnosis of fault simulation using different techniques on fault simulation of PCI. The contributors are as Priyanka Garat, myself, Shikha Devi Katharia and Sushant. In this presentation, we shall walk through the following points. Our main motivation to achieve maximum fault coverage report using PCI example, then an overview of an architecture of fault simulation, different stages of fault simulation, what all status are seen at different stages of fault simulation. Further, we shall proceed with our evidences and lastly, I'll summarize it. Fault simulation is used to replicate the typical sources of failure and analyze them using EDA tools. It includes a testing structure using different fault simulation algorithms, and these algorithms help us to gain insight into a functional design and ensure maximum coverage quality testing. The current EDA tool for functional verification validates the design outside the stimulus integrity, whereas in case of fault simulation, it helps us to analyze design with potential stimulus which are present in the design, and due to various and this can be analyzed with the different techniques which are being present in fault simulation, and these defects can be as environmental defects or design defects. Once these defects are being overcome, we will be able to achieve an fault-free design that is at an initial stage of manufacturing of an SoC. So below, that is a center diagram, highlights the feature of fault simulation. It typically helps to measure the effectiveness of test patterns. It provides valuable information of the design to inject the faults at various nodes of the design. Different possible nodes are being hit and validated using different algorithms of the design. The functionality of the design can be achieved and validated along with the manufacturing defects. Now these techniques can be used to generate coverage report based on the fault signals listed in the test bench. Over here we are using PCI example to achieve the fault simulation maximum coverage report. The center diagram reflects the PCI design. Over here there are different, it's a physical layer of a PCM, but we are trying to cover only few modules of it, that is serial to parallel converter, encoder decoder module, elastic buffer and many more. And then these modules are used to cover all the nodes of these modules and to hit a maximum fault coverage. So now the diagram shows the top level working of fault simulation. In this diagram we can see that there is a GM, that is a good machine. This machine replicates the exact working of the design which is being passed to us, and it gives the stimulus which is being expected from the user. Below that there is an FM, that is faulty machine. Now this faulty machine is being generated by using SSF file. Now one may think, what is this SSF file? This is a standard fault format file. In this we are going to list out different signals of fault, and these lists will be including all the signals of modules. It can have signals as in wire, vary, array, port, and these are being hit in the injected in the design. Then different techniques are used to simulate these all faults, that is serial techniques, parallel techniques. Once these techniques are being applied, we get an FM, that is a faulty machine. Now results of both, that is good machine and fault machine, are being taken and compared. The comparison is done on FS strobe. So based on the comparison result, we are able to tell the fault coverage functionality, that is whether it is ND, DD, PD. Now I can say this particular fault is ND, that is the stimulus is matching for both of them. The expected value is like 0, 0 or 1, 1 for strobes of good machine and fault machine. Then these particular signals are listed as ND. Whereas if the values are mismatched, let's say 0, 1 between good machine and fault machine, then we are listing them as DD. And if we say that if the values is mismatch as X, Z and 0, 1 for fault machine and good machine, Then according to this functionality, the fault signals are listed as PD. The fault signals which are being listed are also, we can say that the fault models, rather than fault models, are being categorized into two different parts, that is stuck at faults and transient faults. Now stuck at faults are as stuck at 0 and stuck at 1. These two types of faults are being injected in different nodes. These nodes are as ports, then vary, wire and array. And transient faults. Transient faults are as like we are injecting this particular fault for a limited period of a time. We can specify that according to the user requirement, and these transient faults are being injected in type of flops. Further slides, I would like to ask Shikha to continue the presentation. She shall give an overview about PCF fault simulation architecture. Thank you.
Hello everyone, this is Shikha from Silicon Interfaces. Thank you Priyanka for giving us brief idea what is fault simulation, what are the techniques of fault simulation, what are different fault simulation models. So I would like to continue further. What are the PCI fault simulation architecture? The architecture determines a detailed process of implementation of random fault patterns compared with a good machine and injection and detection of fault. Here you can see in the diagram, it consists of, like, it goes through a following four process in this architecture. First is like we are compiling the design with fault simulation switches. Then we are passing the SSF file. This SSF file contains different nodes of the design where the fault is getting injected and what value of the fault we are injecting, whether it is 0 or 1, and what type of fault, like whether you are passing port fault, flop, vary or wire. Along with that we are passing the stimulus, and the stimulus can be VCD or EVCD. Then we are running the fault campaign manager. But for the fault generation, the design database is getting created because of the compilation of the design. And this design database is further at fault simulator. It goes through a fault manager and the command script is run. This fault manager consists of testability and the run simulation. That is a fault simulation. At testability, once after having the toggle simulation, where the different nodes of the designs are getting toggled with the different values what we have injected, further it goes to testability, which is nothing but codes. And it runs the fault simulation based on the concurrent fault simulation engine, distributed fault simulation engine and the serial fault simulation engine. As serial fault simulation is much slower than concurrent fault simulation engine. Here then once all these stages are getting completed, coverage reports are getting generated at all three different stages, like fault generation, then at the course, which is testability, and then at the fault simulation. These reports are because of the design database DB is getting compared with the fault manager using the fault simulation database. Further we'll discuss about what are the different fault status at different stages. Right now we cannot see the status at fault generation and the testability, and those status which I am going to tell you right now, like NA, which is not attempted. This is a fault status which we by default define in the SSF file. And further you also have the fault status like untestable fault. Those status are UU, UB and the UT, where the UB stands for untestable blocked, UT is untestable tied and UE is untestable used. At course you get different fault status like NA. You also get the fault status like NC, NO, where NC is not controlled and NO is not observed. These fault status are like observed before getting propagated to the strobes, so it's getting consumed. So these are nothing but, and at the fault simulation this NC and NO gets converted to ND. The status which are seen on this screen are the fault simulation status, which are PD, ND, DD and NC. The PD is potentially detected. Here the value of good machine and the faulty machine values are not matching. But here the FM has detected the X and Z values for the known values of good machine. Now ND fault status, ND is not detected. Here the value of faulty machine was never different from the good machine, and the value of good machine and the faulty machine are matching, so those are considered as not detected. Then we have the status as DD, which is drop detected. This fault status indicates that good machine is having a value of 0 or 1, and on the same side the faulty machine is having a different value, like for the 0 it is having the value is 1. So those type of fault status are considered as drop detected. Further we have NC, which I have told priorly, which is not controlled, and NO, which gets carried forward from codes to fault simulation. and even the untestable fault also gets carried forward from fault generation to codes and to the fault simulation. This represents the test bench of the PCI code. It consists of different instantiation of the DUT models like PLL model, serial to parallel converter, and the elastic buffer. And on these models, the different fault have been injected and with different values. Then here we have shown what are the strobes we have defined. Here even you can have the DUT as an instance which can be defined as a strobe, or you can have a different ports like only a signal output ports which can also be defined as a strobe. So here we have taken the reset, TX, RX detect, PCI serial RXA, DUT elastic buffer as the strobe signals, which we are going to compare it with a good machine, and based on this the different fault status are getting generated at fault simulation stage. Also you can define the FCM detect, what are the signals which can be defined over here. So here we have defined like elastic buffer, half adder, overflow, underflow, which comes into a elastic buffer DUT instance. Here you can see an SSF file. SSF is a standard fault format file. Here it has been encapsulated inside the fault list. Instead of fault list, you can also have the fault generate, and the default status which you can define is NA, and the what value to that particular hierarchy of the design you are passing, 0 or 1. So this is how one can define the SSF file. Also, if one wants to generate the whole hierarchy of the fault and want to inject the fault, so they can also define like top name of the top model dot and the star star. So this what this will do, this is going to generate the whole fault list of that particular hierarchy of the design and that whole hierarchy. This is a way of defining an SSF file for the fault simulation. Then we have the coverage. Here you can see the total faults which we have generated is 1750, and all of them are the prime faults. So prime faults are the faults which get carried forward or which goes into a fault simulation. Here you can see the drop detected we have got the percentages 52.17, and for the not detected we have got the percentages 47.83, which is total, if you do sum up, it's approximately 99%. I would like to hand over this presentation to Priyanka again to give the conclusion of the fault simulation, what are the points have been covered, and give the overview of the whole presentation.
Thank you, Shika, for giving a brief but informative idea about fault simulation, its techniques, and many more. Now, I would like to conclude a presentation. So, as you saw, we used PCI as an example for injection and detection of faults on different fault simulation engines like concurrent and distributive fault simulation engines. We analyzes this fault status in terms of drop detection, potential detect, and not detect, as done as discussed. Different coverage reports are being generated at different stages, as we saw, that is at FGen, then codes, that is testability we can say, and fault simulation. Based on the simulation of this, fault signals are being done. All this is done using an EDA tool. The example which we used almost gave us approximately around 97% of fault status. Hence, by detecting all the faults at various nodes of our design, one can be more confident on the functionality of the design, which can help us fix the bugs or faults which are being generated at an early stage of manufacturing this SoC. Thank you.